So my talk today is on basically HoloBlade, which is the intention is to basically come up with an open platform for driving spatial light modulators for holographic display applications. Why is it not working? There we are. So firstly, just a quick recap on what exactly a spatial light modulator is. So spatial light modulators are a type of liquid crystal display which modulate the phase of light. But they can also modulate amplitude, but specifically for phase modulated holography, we're interested in devices which modulate the phase of light. And by being able to modulate the phase of light, you're able to introduce diffractive and interference effects, and that allows you to produce your holograms in your various applications. The thing is that contemporary devices are not very accessible. They're extremely expensive, for one. So just as a case in point, just before this talk, I went into Thor Labs and I had a look, what's the cheapest SLM you've got? And it's still $12,500 US. And that's like, it's not a completely fair comparison, but it does illustrate just exactly how pricey these things are. And then finally, because they are quite expensive and bespoke and exotic, a lot of the time the interfaces are very much unstandardized and proprietary. So, so you can't just take one SLM and switch it out for another one. You need to make sure that you're using a specific interface with specific driver boards and with specific interfacing software, and it very much frustrates research. So the motivation for this particular piece of work is to try and streamline all of that and put it into one particular standard to make research easier. So in order to actually do this, the key enabling technology is obviously the SLM. And I personally have access to a large number of very low cost ferroelectric SLMs. So I've basically been using them to, as the SLM for the initial implementation of HoloBlade. In the future, I foresee the spec being extended to support multiple SLMs, but you need to start somewhere. So the particular SLM, it's a binary phase SLM, so you either get pi or zero phase. It's 1280 by 1280, so it's a reasonably high resolution, 5.6 micron pitch, and it can run up to 2.2 kilohertz, so it's particularly fast. So I'm going to go on and talk a bit more about the interface I've designed. One thing which I think technically is quite interesting and is worth highlighting is that a lot of the comms interface has been implemented in an FPGA as custom synthesized logic. And actually to do that, we actually used Python and a tool called MyHDL, which auto synthesizes the logic. So I just wanted, and that's been very good to use. So I just want to put in a cheeky little plug for that here. Anyway, so talking about what we actually did, in order to build the full driver stack, starting from the bottom, you need to basically, well, you have your SLM, then your SLM needs to communicate with your custom driver electronics. So we built a custom board to communicate with the SLM. Above that, on the actual custom board, we have our own FPGA where we've implemented all of our own higher level logic to marshal the data as it comes from the PC. And those comms are using USB 3. And the USB 3 is then talking to the PC where we've put together a bunch of PC drivers, which then talk to a GUI application that we've put together to actually demonstrate the application. So just going through that again in a bit more detail, on the top right, you can see the custom electronics board that we've put together. The SLM itself is connected via that flexi ribbon cable. The majority of the work for the project actually ended up being in the FPGA logic. And you can see that in this block diagram here. So the communications between the PC and the custom driver electronics have been implemented using an FT601 chip, which is FTDI's USB 3 chip. So that gives us up to 5 gigabits per second of bandwidth, which is enough to achieve the timing requirements, the throughput requirements that we actually want. That is then talking to a custom USB 3 controller interface that we've put together in the FPGA. the data goes from the controller interface across a dual clock FIFO. So one of the difficulties with this design is that there's a split clock domain. So most of the display update logic runs off the same clock as the SLM, whereas the data to come from the PC runs on the USB 3 clock. So actually marrying those together is quite difficult. And this dual clock technique handles that quite elegantly. And then as we go towards the SLM, we basically have the logic implementations of how to update the specific SLM controller. So that's all been implemented as a discrete update timing controller and as a discrete display data controller. And then there's a couple of other supporting little bits on the actual PCB itself. So there's some power circuitry and there's an external oscillator just to make sure that we get decent timing. In terms of what we've actually put together, you can see it together here in a bit more detail. So the custom PC, so we've put together a custom mechanical mount for the actual PCB itself. So we've done the custom electronics, we've done the custom mechanical mount that's been FDM 3D printed. That all slots in together relatively well. There's a bit of glue at the top. We need to do another revision, but it's quite easy to integrate into optical rigs. So this is a standard Thor Labs cage mount system. It just slides straight on. Underneath, we've actually put a standard optical rod mount. You can't really see it here, but it lets you just screw it onto a standard optical rod, and it means that you can just really, really lock the whole thing down, and it will auto align to your optical system just based on its geometry, which is really good because these systems are incredibly sensitive and you just need to make sure that everything's as secure as possible. The SLM itself is a press fit interface into the front of the mechanical housing. So that just slots in there nice and tight and doesn't move anymore. And then there's a flexi ribbon cable between the SLM and the electronics board, as I talked about earlier. There were a lot of issues had with actually mechanical strain damaging the flexi. It's quite a trivial thing, but it ended up a lot of time got spent on actually making sure that the flexi itself was appropriately strain relieved. So this current design handles that really well. So this is not version 1. It took a couple of iterations to get it right. Right, now, moving on to results. So what you can see on the left is a custom optical system that has been built up around the SLM. And on the left, you can see clear diffraction effects. And so this is a standard 4F imaging system. You just basically shine the laser at the SLM and then imaging on a separate imaging arm. And you can see that there's a large zeroth order in the middle because the polarizers aren't set up properly. But beyond that, there's a whole bunch of diffractive effects moving across to the side. And that's demonstrating that the system is capable of producing holograms as a sort of initial proof of concept. The particular test pattern being shown on this image for this particular scene is a checkerboard test pattern. So you can see that on the bottom right. There's been because SLMs modulate phase rather than amplitude, you can't actually see what they're displaying normally. So there's just a piece of polarizer film on the top, just so you can actually discriminate that checkerboard pattern, which is a bit blurry, but you can see it. Anyway, so in terms of summarizing it and next steps and things we would like to do. So we've put together an initial implementation for HoloBlade. It's a full open source SLM driver stack. All the bits have been published online, so they're freely disseminated. One thing that would be very nice with this is for it to grow into sort of an ecosystem of holographic and SLM related support technologies. So because this entire driver stack is open and because people can build on it, it means that more advanced use cases such as on-the-fly data compression between the PC and the SLM, that they can potentially be done because they can tap into the existing driver stack, which is already there. So things that would be very interesting would be data compression, variable refresh rates, dynamic bit widths, some of these more advanced display features that we are actually seeing with contemporary displays in TVs, things like HDR and gamma correction, stuff like that. Shifting those into holographic display technologies would be really interesting. And HoloBlades is, I feel, a really good framework to actually do that. In terms of stuff to be done in the near to medium future, the first one really is to use the system in anger as much as possible, and just to get it in as many systems as possible and actually refine it. Secondly, it's currently using a custom C++ interface driver that we've put together. What would be significantly more useful as a research tool is if that was to be extended to include a Python and a MATLAB interface, and then you'll be able to drive your SLM directly from MATLAB. So that would be incredibly useful. And then finally, in the future, we would like to expand it to support additional SLMs. That would be quite a lot of work, but would be the sort of thing that I think really demonstrates the value of the platform. So yeah, anyway, that's it for HoloBlade. Any questions?